get into it. Alright, so welcome back everyone. Today we're going to be talking about pointers. So our previous addition to the compiler was function calls. So we've got this function Fred here that is going to compute the factorial value of that integer x, and so we can call that. We did not get around to adding in arguments to the functions yet. It's going to happen eventually, but I'm not going to do it yet. So today what we want to do is we want to add in pointers. So hopefully you're familiar with pointers. If you're not, I suggest studying up on your own. But for example, we've got this code sample right here where we initialize an integer a to be 18. We get an address of it, which we store into int pointer e. We dereference that with that dereference operator, that star, and then we print it out again. And so referencing and dereferencing, they nullify each other. So we're going to get 18. Do the same thing for C down in that second little block there. And then in the third block, we're showing off that we want to have multiple depth pointers. So one thing is that ACWJ, when they do their pointers for the first time, they do not add support for multiple pointers, and we are going to, because let's get that out of the way. Let's do it all at once, I think. It's a really cool feature. Pointers are just, they're so fundamental to any large-scale development that you'll do in C. In the future, it's going to let us pass more versatile objects into our functions so that we don't have to pass by value all the time. We'll be able to call malloc whenever we start supporting the C standard library. The issue is that to accomplish any of this, we basically have to refactor our entire number system, which is going to be really annoying. But we got to do it sometime. I wanted to get it out of the way earlier rather than later so that we don't have more code to refactor. So here's the plan. We need to add in new tokens, one for ampersand, and one we're going to add a dereference meta token. We already have a star, so we need to add some other meta token to let the code generator know this is different. Don't treat it like a regular multiplication. We need to mess with our number and our LVM classes so that we can store information about pointers. We need to add a type parser so that we can check for pointer declarations. We need to update our expression parsing so that we can handle unary operators, specifically unary pointer operators, but it's going to lend itself to doing regular unary operators in the future. We need to update our register loading code, and finally we need to add in generator functions for addressing and dereferencing variables. So I'm not going to show you the code for adding in the new token for ampersand. That's easy. We know how to do that by now. But we do have this issue with our dereference token. But we can't use the star token again. The times operator already uses a star symbol. So because we're building an abstract syntax tree instead of a concrete syntax tree, we want to be encoding ideas about the program. We don't want to encode every specific detail about the program. That's called a concrete syntax tree. We're not building one of those. So because it's abstract, we want to encode ideas, and so the way we do that is we're going to add in a dereference token, which doesn't print out a star when you print out that token value, but it's going to represent the idea of a dereference operation. And in a second, we'll see how we can use both of those in tandem. So let's look at numbers and LVM values. numbers and LLVM values, it might not seem like it, but they represent almost the same thing. Our number class is going to represent data that's flowing around in the compiler, or data that will exist in the runtime program, but when it's in the number form, that's still in the AST parsing area of the program. And then an LLVM value is the code generation part of that number, of those numbers and stuff like that. They kind of represent the same things, and the issue is that right now all they can really handle is numbers, and we want to update them so that they can handle pointers as well. We want our number class to be able to know I'm holding a number pointer, and our LLVM values saying I'm holding a number pointer. And ACWJ accomplishes this by actually adding in specific types: int pointer, char pointer, long pointer, on top of the existing int and char types. The reason that's suboptimal is because what if I've got a bunch of types? What if I add more types to my language? I have to add in new pointer types, but then what if I have a struct pointer? Like, we can't add in a type at compile time. We can't add a type into our compiler if it's user defined, right? So we're going to forget about adding extra types for pointers. We're going to all the types are going to be the same as they have been, except they're going to store information about pointers in them. And then my first approach to solving this problem involved having a stores pointer bool field inside of the number and the LLVM value classes. The reason that's so optimal is because what if we want two layers of pointers? Like what if we want an int matrix instead of an int array? That requires a double pointer. So having a stores pointer bool field is only going to allow us to have depth 1 pointers, which we don't want. Let's get pointers, the whole pointer stuff out of the way right now. Let's not worry about it after this lecture. The solution to that is that we have this pointer depth int field that's in both classes. So regular integers and characters and whatevers, they're going to have a pointer depth of 0. Int pointers are going to have depth 1. Int pointers, like an int matrix, that's going to have depth 2, etc. And that generalizes really well. We can update that pointer depth field just by regular old addition or subtraction whenever we use address or dereferencing operations. And so we can do all that inside of the parser and inside of the code generator, and that's wonderful. And I guess I'll show you, pointer depth. Yeah, so LLVM value, we've added in a pointer depth field. I've added this references property that just says give me as many stars as we have a pointer depth. So if you call LLVM value that references on an int pointer, it should give you 1 star, and so on. And that just helps with printing out our types in the generator part of it. Let's see, where else do we use pointer depth? Class number, same thing. Numbers also got identical references function. And let's talk about type parsing before we get on to the next thing. So with our new tokens and with our new number type updates, now we can parse pointer variable declarations. So like int pointer x semicolon, int pointer y semicolon, int pointer z semicolon. Those are pointer declarations, and now we can type we can parse those. So I've added in this new function called match type, and it's nothing that we haven't done before, really. Well, part of it isn't. You've seen this line before. So we're just going to match in a regular old token type. We want it to either be an int or a char. Those are our type keywords. And then, as long as we see that the next token type is a star, because a star that's the actual character of a star, asterisk, whatever. As long as we see one of those, we are going to consume it, which is what match token does, and then we are going to increase our pointer depth, which is just an int that we have right here. And then once we don't have any more stars, we're going to return a number that converts your token type into a number type. It's going to default initialize it to 0, and then you're going to give that pointer depth to the number. So now if you have int pointer x, its match type is going to match the int pointer part. It's going to return a number that says you've got an int, an I32 pointer. So that's the LVM type that we're going to recognize. And we can look at where match type gets used. For example, in declaration statement, which makes sense. If we're declaring a variable, we should check for whether or not we're declaring a pointer. So we're going to match a type. It's going to give us this num object, which is a number object. And the reason why we're messing with its pointer depth right here is, remember that when we declare global variables, we have to store into them and we have to load from them, which means that they're actually pointers themselves. So if you declare int x, the LVM representation of it, it's going to say, declare global x, but then that x acts like an int pointer that you have to save to and load from. So here we're just going to increase the pointer depth by 1. We're going to add it to our global symbol table. And so that's good. That's what we want. We want to treat x like a pointer, even if we are saying we're declaring it as an int. And then, so we declare global. We used to give it a number type. We now give it a number because the number has to store that, that pointer information. And so now, if we look at LVM declare global, I need to load this big diff. LVM declare global. We can see that it now accepts a number, and it's going to print out the number of stars appropriate for that. So I think that's all good. We can look at some other places for match type. There's no other places for match type. We should technically have it in the function declaration area. We can't really support that yet because you got to remember that these pointers are stack pointers, except for variables, but I'm not worrying about that right now. We've got, stack pointers. Stack pointers are not preserved when you return them from a function. So to update the function declaration to check for pointer types wouldn't make any sense right now. Not at least until we get malloc working, right? So now we've got this issue where we want to parse unary operators and expressions. Normally when we've added operators, we would just add entries to our precedence table and then boom, handled all for us. That's what we love about prat parsing. However, we have to do some static semantic checking to make sure that programmers can't use pointer operators illegally. And so if we just added regular old unary operator support without any checking, then you could say something like int x, okay, that's fine. Int y equals pointer x. Well, that should not be legal because, these are dereference operators and this is not a reference. So that's bad. We don't want people to be able to do weird stuff like that. They should do what's right. And then you've got ampersand y. Well, those are address operators. Ampersand y, that's going to be an integer, like an integer constant. So you can't take the address of an integer constant, so we shouldn't let programmers write that. And so we need to explicitly say we're expecting this kind of behavior when we're parsing unary operator expressions. So I've written this function called prefix operator pass-through. Let's look at that. Prefix operator pass-through kind of acts like a wrapper for the parse terminal node function that we used to call right here. So this is in our Pratt parsing loop, where we'll get a terminal node as our left thing in the expression. Now we're going to call prefix operator pass-through because in a binary expression, the thing on the left could be a pointer operation, and so we need to parse that right away. So let's look at prefix operator pass-through. So we get the current token type of the global scanner. If we've got an ampersand, so that's the address operator, we are going to consume that ampersand by scanning. We are going to recursively call prefix operator pass-through. The reason for that is because when we go down here, when we parse the next token, we are expecting an identifier because you can't do the addresses of all that stuff. Eventually we'll want to do offsets and whatever, but right now we're just going to take addresses of individual identifiers with no modifications. So that should trigger this else statement down here, which says, well, if I don't see an ampersand and I don't see a star, well, let me just parse a regular old terminal node. So that's what this recursive call is for. We're expecting an identifier. If we don't see one, we're going to throw a syntax error. We are going to take that AST node that we got back from prefix operator pass-through. We are going to change it from an identifier token type into an ampersand token type, but its value is still the identifier that was parsed by the identifier parsing stuff up in parse terminal node. We increase the pointer depth by 1. I'm going to come back to that, and then we return that node and we're done. Next, on the dereference side, so again, we scan our token, we do a recursive call, and we are expecting to see an identifier, or we are expecting to see another dereference operator. So if we have int pointer x, it is valid to say like 1 plus star x, and so that's dereferencing it twice. So that's okay. So this token type should be called dereference. I'm sorry about that. I'll rename it, but we're saying dereference operators have to be succeeded by dereference operators or variable names. So same concept as before. We are again gonna modify this pointer depth, and then we are going to return an AST node. So that is our unary operator parsing. Good? Good. So we got to talk about loading registers now. In the past, we had LVM loaded registers, this big list of all the registers that were loaded and were ready to be used for computation. And we used that to determine what was loaded and what wasn't. That's not going to work anymore. And the reason why not is because now it's ambiguous whether something is loaded or not. If we have operations on pointers, 2 pointers, and we operate on them somehow, it's not sufficient to just say, well, the load depth, the pointer depth should be 0, so load them until we get to 0. We need to have some more robust way of loading registers properly. And the solution is to add a new input. So first we got to get rid of LVM loaded registers. Not going to use it anymore. The solution is to add this input to LVM ensure registers loaded that specifies the exact pointer depth that we're expecting to be considered as loaded. So let's look at LVM ensure registers loaded. So yeah, I've got this load level right here, pointer depth to which registers should be loaded to, and it simplifies part of our code and it makes another part of our code more complex. But if the pointer depth of a register that we're looking at matches what we're looking for, then we can say we found it and we're good. And then if, yeah, this is the same. If all of our stuff is loaded, then we're already good. But otherwise, we are simply just going to load in that new value. That just deals with printing out the type of all of that stuff. So don't worry about that too hard, but that solves our register loading problem. And for most intents and purposes, we do want a load level of 0. All of our arithmetic stuff, we don't want multiple pointers to be added together right now. We just want regular numbers. So having that load level 0 does work just fine for what we're doing right now. And so now we've got some new generator functions. Let's take a look at those. Post-amble get address. So this is for the ampersand operator getting the address of a variable. What we're going to do is we are going to, we're given an identifier, because remember we had an identifier node and then we just switched its type to a to an address operator. But it keeps that identifier as a value. So we are going to use that identifier to grab it out of the global symbol table. Make sure it exists, make sure it's a number, whatever. Normal linter stuff, don't worry about it. We are going to get another local virtual register. We are going to create an LVM free value, or an LVM value with a virtual register, give it the number type, give it the pointer depth, we're good. We do have to perform stack allocation because we are going to be storing literally just at identifier. We're not going to be doing anything. We're just going to say whatever this identifier is, we're going to store it into this register. And because that variable is stored as a pointer, its address just gets put into our new virtual register, which is exactly what we want, right? And that's it. That's all we have to do for addressing. So that's very nice. And then for dereferencing, we get another local virtual register. We decrease our pointer depth, and then we are just going to load. We are going to load our whatever was passed into the dereference, this value, into whatever our new virtual register is, and that's just going to decrease the pointer depth and one single load, and that's good. So boom, that is wonderful. That is all we need to do really to add in pointers. I say all we need to do, it's a lot of code to write, but for that amount of functionality that we get out of it, I think it's really a bargain. So let's look at some code, huh? Check out 10, 11, 12 pointers. Oh, what did I change in here? I'm just going to stash that. Alright, so let's check out pointers. I've added in a new test 9. So this is what we saw at the beginning of the lecture. It's got our regular pointers and dereferences, and then we've got a depth 3 pointer that we mess with. So Let's do scripts, run, examples, test 9. Let's see. Okay, let's look at test9.ll. So, whole bunch of loads and stores, just like we expected. But look at all that. Look at all those beautiful multiple pointers that we didn't write any special logic for, and it's all handled, by our general purpose code. So let's see, clang test9.ll. And let's look at the examples so we know what we're expecting. This should print out 18 because it addresses and then dereferences. This should print out 12 because, again, it addresses and dereferences. Here we assign G to be 5. We address it 3 times, and then we dereference it 3 times. So it should just print out 5. So we should see 18, 18, 5. Or 18, 18, 12, 12, 5. I should have said that before, but here we go. And that's it. That's all we needed to do. So that's good. We do have optional homework this week, although it's not in the slides. I'd like you to implement while else loops and for else loops. Those exist in Python. Go look them up if you're not sure how they work, but implement those, and that's your homework. So thank you very much, and have a good rest of your day.